Welcome back, welcome back, welcome back. I'm Miss Lisa, and this is my YouTube channel for everything that I want to talk about with science and math. And today we're going to be talking about chemistry. The chapter in the book I'm looking at is electrons and atoms, but what I think of this is I call it quantum. So, I mean, it's not like just I call it quantum. When I've taught it for years and years, this is the chapter in the book that normally says quantum physics or quantum chemistry. So what this is talking about is we have already learned that the parts of an atom. We learned that outside of the nucleus is the electrons, and we have the nucleus that is made of protons and neutrons, and protons are neutral, or protons are positive, neutrons are neutral, and electrons are negative. Okay, we've already learned about all of that stuff. But this is we're going to talk about in this video a little bit of the history of how we got to the model of the atom we currently use, and then what are the electrons doing in the atom. And that's where we overlap with physics in quantum, and this is really quantum physics. Okay, so we'll get there, it'll make sense. All right, so first of all, let's go back and talk about the very first idea of atoms was a Greek philosopher named Democritus, and he was standing on a beach and he said, this beach is one thing, but it's made out of many things, many little pieces of sand. I am one thing. I wonder if I'm made out of little bitty pieces of something that can't be broken down further. I will call them atoms. An atom is Greek for indivisible. So when you say the pledge, you can say one nation, atoms for liberty and justice for all. One nation, indivisible, with liberty and justice for all. So that's where it first started. Now, then came along the chemistry dark ages, the alchemists, who they were kind of bordering on witchcraft and trying to change lead into gold and things like that. They were get rich people trying to use a little bit witchcraft, a little bit science, and make some money. So, but they really made a lot of our glassware and a lot of our techniques, a lot of our equipment, and some of the methods that we use now, they developed. So, but that wasn't really science. It wasn't really chemistry. It was alchemy, and it wasn't the modern age of chemistry as a science. Okay, so then came along a guy named John Dalton, and there's a video that you can go on YouTube and watch. It's called Adam's Ring of Truth, or Ring of Fire, Ring of Truth, by Dr. Philip Morris. And in it, he says that there is a graininess to matter, that there is a microscopic world of the atom that we can see in the macroscopic world. And I teach public school chemistry, and I will be making my class, hold on, some Apple little message popped up over there, so I'm touching this, sorry, because I'm doing this on my phone. Anyway, that there's a graininess of matter that is present in the microscopic world that we can see in the macroscopic world. And I'll be making my students in public school watch that video and answer questions on it, and you should watch it too. If we were in class face to face, I would assign it to you. So search YouTube for it. I think it's Adam's Ring of Truth, and the host, I think, is Philip Morris, which is like the tobacco person, but this is a scientist who worked on the Manhattan Project, which is where we made the nuclear bomb in World War II. But anyway, so that idea that the atom is reflected in the macroscopic world is something that started coming about at the time of John Dalton. So John Dalton came up with the atomic theory of matter, which was everything's made out of atoms, these indivisible particles. And there's more to it than that, and we'll talk more about it. Either we already have or we will when we talk more about the atomic theory of matter. But this is more about the models. And what he said the atom was like was a billiard ball, a pool ball, that it's round and hard and it can bounce off. And and that's all he said that, you know, it was indivisible. That is the smallest piece of matter. Well, it's called the atomic theory of matter and not the atomic fact of matter, because John Dalton was right, but he wasn't completely right, and we have added to it as we've learned more. So models in science are things that, and theories are things that can be added to as more is discovered. Okay, so he was the first one. Okay, then the next person, they started figuring out a little bit about subatomic particles. So next came J.J. Thomson, and his model was called the plum pudding model. You can tell this was a long time ago. That was a popular dessert, not so popular anymore. But if you can imagine some vanilla pudding with raisins in it, that's what they thought the atom was like. They said that it was like, that they could tell that it had some charged particles in the pudding, and so they thought that the pudding was positively charged and that it had electrons, negatively charged particles embedded just randomly throughout. It was from electricity experiments. Remember Benjamin Franklin, 1700s, people are starting to figure out about electricity. They know it's charged particles. We know about static electricity, lightning, and they're starting to learn about that, and they figured out that these charged particles were coming from the atom. Well, a guy came along and he was going to prove that the model, the plum pudding model, was right. And so he was just going to do an experiment to prove it. And his name was Rutherford. And what his idea was is he took gold foil. It's like aluminum foil but made out of gold. And because gold is so malleable, you can make it really, really thin, just really about 10 atoms thick. And he had this piece of gold foil, and they had made ray guns at this point. They made things that they didn't really know everything about, and they could shoot alpha particles, which are just these little positive particles out of their ray gun. They were going to shoot the atoms with the ray gun, and all around it they put like glow-in-the-dark stuff. And whenever the ray gun hit the glow-in-the-dark stuff, it would make a flash, and you could see it. And he made his graduate students go to do it because he wasn't even in there when they did the experiment, because he wants to stand in the dark and count little flashes. So make the students do it, you know, graduate students. So what he expected to see is, imagine if you shot a gun at pudding, what would you get? A big old splat on the wall, right? So he expected to get a big splat of glow-in-the-dark kind of stuff on this glow-in-the-dark thing that went around. That was like, they didn't paint the walls, it was a piece of equipment that went in a circle. You can look it up. There's pictures of it on the Google. You can Google it. So they're standing around looking, and what they found was like 99.9% of the time that the alpha particles would go straight through the atoms and hit over and over again in one place. No splat, over and over again, one place. Every now and then, it would be like it hit something and get deflected, and it would go off at weird angles, and it would even come straight back at them. They were absolutely astounded. Are you astounded? You should be absolutely mind blown from this experiment. And this is why. Because that meant that 99% of an atom is empty space. It goes straight through without hitting anything. Only a tiny, tiny fraction of the atom is anything, and that's the nucleus, and it's positively charged. So when the ray gun got deflected, it was hitting that positively charged nucleus and getting deflected. And because the alpha particles are positive and the nucleus is positive, it would be repelled and could be deflected even straight back at them. This is why this was so mind-blowing. Because the atom is empty space. If the room you are in right now were the atom, the nucleus would be as big as a printed dot of the I or a period on the page of the book in front of you. Everything else is empty space. That means you are empty space. Everything you know and love and eat and pay money for is empty space. There is nothing to stop this hand going through that one except energy. It's energy. Your energy more than matter. Yeah, we're matter, but it's energy that gives things substance. He said, Rutherford said, and I'm paraphrasing his quote, but he said he could not be more shocked if he had taken a shotgun and shot it at a piece of tissue paper, and what he in the bullets, whatever is coming out of there, would come straight back at him and hit him. He said that would have been no more shocking than this was. He discovered that everything, our world, our atom that makes everything up, is 99% empty space. 99.9. It's nothing. So, but I always comfort students with these words. That's okay. You knew you were more than the atoms that make you up, right? There's more to you than matter. You're important. There you go. Are you all comforted now after finding out your empty space? All right. And I don't want to hear any jokes about someone's head being empty space. All right. So that was Rutherford. So then they came the Bohr model. And this is what you think of with the Jimmy Neutron model, is what I say it, or the planetary model. It's that the nucleus is in the middle, and the electrons are orbiting it like the planets do the sun. But so actually it was Rutherford who first said the planetary model, but then Bohr changed a little bit, where he started realizing that the electrons hang out in different energy levels. So we started getting the Bohr model. Now the modern model, and there are a lot of different people who have added to it, because once knowledge starts, then everybody jumps in and starts learning new bits of it, and you can learn a lot more about it. And if we had more time face to face, I'd tell you a lot more stories. But what we have now is called the quantum model, and that is that the electrons hang out outside the atom, around it, but they don't go just in orbits like the planets. They hang out in clouds, and these clouds are clouds of probability of where you will find them. Okay, now then, here's the next idea. How the electrons move. Okay, these clouds, they're called orbitals, that are around the nucleus. The electrons hang out in different ones, and they fill by energy. So the ones who have less energy are closer to the nucleus. The ones with more energy hop out to more far away orbitals. Okay. Now, there are no stairs between the orbitals. They have to jump, and that jump is called a quantum leap. There used to be an old show in the 90s about somebody time traveling with quantum, and my students would always say, does that have anything to do with this? And I remember saying, I've never seen the show, but I don't think so. Well, the more I learned, actually, yeah, there's this connection. There's a lot of experiments going on right now with time travel. I know, you're laughing, but it's true. I keep up on the current, chemistry research. And last summer, they were going to do this experiment in Tennessee at the lab there, the Oak Ridge lab, where they do a lot of nuclear experiments. And this is sort of nuclear chemistry. They were going to see if they could get electrons to teleport or to time travel. And they thought they could do it. They had it all set up, and they were supposed to do it last summer, but I never heard anything about it. But we had the big COVID shutdown, so the experiment might have got put off, because I never heard whether or not they did it or not. So, but I just heard they were going to, and I was like, oh, quantum leaping stuff does have something to do with time. So there you go. All right, you can learn more about it. Well, I don't know much about this. There's people with doctorates and this sort of stuff, and that's certainly not me, but the internet's out there, and you can read more about it. Okay, so the orbitals come in different. So one good comparison to all of this is it's like a ladder, and if you're at the bottom, putting your foot halfway between the rungs will do no good. To climb up a ladder, you have to go all the way from one rung to another, and the electrons are the same way. If they go halfway between they have like half of the energy for a quantum leap, it does them no good. They have to have the full energy for the quantum leap to get between levels. It would would be like if it was an apartment building with no stairs and you were a flea or something that could jump good, better than people, and you had to jump to which level you lived at. Okay, now these orbitals, these clouds where, this is a little physics here, these clouds where the electrons hang out have different shapes. So these orbitals can have different shapes. The one that's lowest down is round, but it's actually in a sphere, and it's called an S room. S for sphere. So like for your hydrogen, it's only got one electron, and it hangs out in the first level that is called the 1s level, because it's the first level and it's sphere shaped. Then the next electron, so hydrogen has one electron. We'll say this is the nucleus and that's the electron. It has one electron in a 1s in the first sphere shaped room. Helium has two electrons, so they double up. They share a room. Helium has two electrons that both go into the 1s room. Now, why don't they want their own room? Well, they like, I'm sure that they have emotions, but at least they have energy requirements. They like not having to go up those quantum leaps. The ground level floor is the best in any apartment building that doesn't have an elevator, right? If you have to go upstairs, you want the ground floor. You don't want to have to carry your groceries all the way up all those stairs. So the next orbital is also sphere shaped. It's on the second level of energy, so it's 2s. So the third, so lithium, I think is the next one, has 3 electrons, and the next one goes into that the 2s room. So you can write where the electrons for an element is. So like if we were going to do lithium, make sure lithium's 3, right? Boron, lithium, boron. I'm going to have to look at my periodic table. I've been teaching all day, and by this time it's like, yeah, lithium's 3. Lithium's 3. All right, there we go. So if we were going to write what's called the electron configuration for lithium, we would write that in the 1s room, it has 2 electrons, so we put a little 2 up there. And in the 2s room, it has 1 electron. So this is the electron configuration for lithium. It tells us what's going on, where the electrons live for that particular atom. All right, so the next kind of room is the next orbital, and it's a different kind of room. It's called a p room. And they say the p rooms look like dumbbells. Now, I don't know what kind of dumbbells these chemists are lifting, but that does not look like a dumbbell to me, but that's what they can say. So like the nucleus is here in the middle, and the electrons can hang out on this side in the dumbbell or on that side in the dumbbell. And it turns out where these sphere rooms are exactly the same, that there are 3 different p rooms, and they have different orientations. They could be on the y-axis, they could be on the x-axis, or they could come out at you and be on the z-axis. So they would go around this atom kind of looking like that. And if you go and Google this, you can see really good pictures of it. But there's 3 different ones, and those are P's. And I don't know, S for sphere makes sense, but P for dumbbell, I don't know what. P for pumping iron, because it's a dumbbell. I don't know. So those are P's. The next kind are D's, and they kind of look like fat pluses. And they can go on the X-Y axis, or they could go between the X and Y like that. Or they can go the other way, so they can be flat against the board or coming out at the board, either way. Or there's another P one where it looks like 2 baby pacifiers stuck together. So there are 5, these are D rooms. D for pluses? I don't know. But there's 5 of them, because it can go this way, and then that way, in that way. You can't see it. And then the baby pacifier thing. So, okay, and then there's another one called F, and they look fuzzy, and that one makes sense. F for fuzzy. Now, this is why the periodic table is arranged the way it is. If you ever notice the periodic table is a weird shape, you would think it would just look like a calendar, but it doesn't. It's got like a tall part, a flat part, another tall part, and some at the bottom. Well, I wish I brought a periodic table, and I had thought about recording this at school and from my periodic table. I probably should have, but I ran out of time because I rearranged my lab on Friday, and it looks great. But anyway, so I ran out of time to make the video at school when I wanted to. But anyway, so if you remember the periodic table, that there is a tall column over here, and those elements fill the S rooms last. So S, there's 2 of them, and 2 electrons can go in the S rooms. It's going to fill that S room last. Then comes a bunch of flatter ones, and those fill D rooms, and there's 10 of them. Because, okay, and remember that there are 5 different shapes of D. There's 1 shape of S, so if you take the number of columns and divide it in half, it tells you how many of that column it is, because 2 electrons can go into an orbital. If that seems confusing, don't worry about it. It'll make more sense the more you do it. Okay, so anyway, then comes the Ds. Then there's another tall part over here, and there's 6 of them, and those are the ones where their last electrons are going to go into Ps. And then on the bottom, there's 14, and those will go, their last electron will go into one of the 7, see how I'm cutting it in half, one of the 7 fuzzy rooms, the Fs. So the shape of the periodic table is based on the characteristics of the atoms, which is based on electron configuration. All right, so take a good look at that in your book, or look on Google, and you'll usually see the S's, you'll usually see the D's, and you'll see the P's, but they usually don't show you the F's because they're just too complicated. Okay, now then, when these electrons jump up these quantum leaps into the different orbitals, normally they just do it to fill the orbitals in order, whichever room is the best one. Sometimes they'll take a bigger room higher up than a smaller room lower down. And so there's a order to which they fill, which the book talks about, or you can learn more about that, but we're not really going to go into it much here, but is based on energy and preference of the kind of orbital it is. But sometimes they can hop up into these orbitals, not just filling them, but because they're excited. Okay, so excited they jump up into a new orbital. They can get excited by heat and electricity. And when they do, they have extra energy they need to give off to go back down to where they're supposed to be. So that's why electrons, why you see certain phenomena, and it's all based on these electrons jumping down. Glow in the dark stuff is stuff that has been charged up by light, and then it gives off that extra energy as it comes back down by glowing in the dark. Another one is another one is like neon signs. With neon signs, and only the ones that are reddish orange are true neon, otherwise it's another gas in there. But with neon signs, they're being excited by electricity, and that electricity is causing the electrons to jump out of their orbitals and or give off the extra energy as photons of light. So that's why you see a lot of stuff like that. Also, even force can cause it. One of the lab that you're going to do in this chapter is you're going to take wintergreen lifesavers, the ones that say Wint-O green, and you need to buy real Lifesavers brand. Get where it's completely dark, give your eyes time to adjust, and then use pliers and crush it, and it will give off blue light. It's so cool. We did it last semester, and some of my kids in my chemistry class said it was their favorite lab we did, was crushing the Lifesavers with with pliers. Also, breathe right nasal strips. I don't know if you've ever used them, but if you wait till it's totally dark and pull apart the packaging, it'll glow. Breathe right glows blue. It'll make blue light as you pull it apart. Kroger brand makes orange light as you pull it apart. Now, I did that with my chemistry students in public school last semester, and we couldn't get the room dark enough for them to see the blue light, but we were able to do the lifesavers, and it was really fun. Also, glow sticks is another thing where you're seeing a chemical reaction giving off light. So this light, okay, now atomic spectra. Okay, when the electrons jump out into light, that each one does it differently. Each element on the periodic table has a different atomic number. The atomic number is the number of protons, but if it is neutral, it hasn't gained or lost electrons, it has not become an ion, but it's just an atom, then the number of electrons is the same as the number of protons. And that number of electrons only fill certain orbitals. So when they jump out or they give the light off, they will only give off certain frequencies. So instead of it being the whole visible spectrum of light, the whole rainbow, it's a broken rainbow where there's only little pieces of light that represent each orbital, each electron, giving off extra energy as photon. So they say this is the fingerprint of an atom because each atom has a different absorption spectrum, or what it shows, or its bright line emission spectrum. So I do a couple of labs with my kids that are face-to-face, if we were face-to-face in class, or my public school kids. What we do is we will use a spectrum tube, and you can order these off of homesciencetools.com. But you look at a light source like a neon sign, and you will see these little lines of color. So for my public school kids, I have different gas tubes, and I have those things that they can look through, and they can see the broken rainbow. Now, there's ways to do it that's a little cheaper. They make these things called 3D Spectra glasses. You can get them off Amazon, Walmart. You can get one pair for about $4 or $5. You can get like 20 pair for $8 and 50 pair for $20, is like if you're a teacher and you want everybody to have them. But you can put those on, they're rainbow glasses. But if you have a pure source where you're not just looking around at full spectrum light, like a neon sign, or there are birthday candles you can buy that burn different colors. The reason why is because they have different elements in them. They'll burn green, which is copper, or sodium, which is a yellow, orangey yellow, soft orange yellow. Lithium is a hot pink. You can look at those with those glasses on, and you will see the broken rainbow. You can see the spectra that way. So it's really fun to do. So you should do it, or if not, at least watch videos where you can see it. Okay, let's see if there's something else. We talked about quantum concept. Light is, okay, photoelectric effect. Okay, so light has a dual nature. Light can be like just a wave going through a vacuum, but it also can act like a particle. And one way we see this is called the photoelectric effect. If you have atoms, of course, and you shoot it with light, electrons can splash off. It can move electrons, the light can. And when it does that, it's acting like a particle. And that photoelectric effect can be used if you ever have anything that's solar powered, like a calculator or something like that, or like those little dancy people that you can get, you know, the hula girl, or we got one for my son when he graduated that was an owl that would bob up and down, but then he got knocked off and broken very quickly, probably because I got him somewhere cheap. But anyway, those things that are solar activated that move, it's because of they use that movement to generate electricity, moving electrons, and you can make these little things move. So they can use that to make a little bit of electric current and use it to power something. Let's see, atomic spectra, de Broglie. There's a relationship between the wavelength, the wave motion of wave and matter quantum mechanics. That's a little deeper than I'm ready to go with that. You can read about it, but just know that you can take a whole college course on this stuff. And when you take physics, you'll learn more about it. You'll learn about quantum numbers, how every electron has its own address by these quantum numbers, how to figure them out. But I think this is going to be enough for this video because we've already been talking 30 minutes. Who's going to watch that? All right. Like, share, subscribe. Science is great. See you soon.